Testing, testing.
I can hear you now.
Oh, you can hear us?
Yeah, I just heard you
Carl?
say test just now.
Okay. All right. Okay. So you've had a lot of time to think about questions now. So who has a question? Victoria, I think you have a question. Oh, wait, we have one here. All right. You're off the hook.
Hi, this is Catherine. I know you can't see me, but now you know a name. So you mentioned that even the satellite imagery, you need to get like a local calibration for it. And I was just wondering how many points of data, like on the ground measurement, you need to get an accurate local calibration.
Yeah, that's a good question. So yeah, it's hard to give I guess a general answer there. So for the example of these global data sets, the Randall Martin's group, the von Donkler et al. Data set that I showed a brief image of. They're using all the ground sites around the world to develop these kind of calibrations, and they do cross validation. They leave out some subset of those ground sites, develop the algorithm using all the other ground data, and then test at the ground sites they've left out, and then they cycle through all the ground sites. And in that way, they're able to at least quantify how accurate do we expect these estimates to be for any given location. Now that's good. It is limited in the sense that where they can't do a validation where there's no data. So they're only saying, in areas where there are ground data, we verify it to a certain degree, and that could be regionally biased because certain areas will have a lot more monitors in them, so it might be performing better in those areas. In other areas, there's fewer monitors, it might be performing worse. I think they do, they have, or certainly people have done that kind of a validation where they say, okay, for this specific region, we know there are fewer monitors, so we're going to restrict our validation to this region and see how well it does there. So it's hard to say, in general how many you need. I think it's kind of a spectrum where, the more you have, kind of the better you can expect to do. There is a trade-off. I've looked at, I looked at it in a paper where, we looked at, Pittsburgh, where we were using low cost sensors. We had a lot of them in the city of Pittsburgh in the U.S. And there was like a trade-off where the first five or so sites gave you a pretty good result, and then your improvements, you didn't really improve by much as you went from 10 to 20 sites, for example. That was that specific case for that specific region. The concentrations were kind of low on average there, so once you got to that level, you couldn't improve very much. So I think that's maybe an open question, and I think the answer will vary quite a bit region to region. How variable is the actual concentrations? For things that are less variable, if you just had one site, you can make that calibration, and it would apply over a wider region. Whereas where conditions are a lot more variable, or for pollutants that are much more spatially variable and temporally variable, you would need more data. So yeah, I can't give like a general answer. I think it has to be tested, and that's, I think, a place where like low cost sensors can play an important role, because you can more cost effectively do those kinds of tests. Deploy a couple low cost sensors and see what results you get, and then kind of zero in on a maybe an answer to that for your specific region and for the constituent that you're looking at.
Thanks, Carl. All right. There's one more question. You got it? Yep.
Please, thank you very much for the beautiful presentation. You have said it's difficult for satellite imagery to take note of vertical distribution of particles. I'm just wondering why it's not possible, because I know that in geological prospecting, you send a signal down the earth. It's reflected back, you're able to determine the location or the distance. Now, you are taking reflections from particles, a signal, let us say, sunlight now. The rays from the sun are reflected by a particle, and the satellite picks that signal. Why is it difficult for satellite to determine the location of that particle? Because if it does know the location of that particle, it will be possible to say or to define the vertical distribution or concentration of particles down the line to the Earth's surface. I'm just wondering why that is not possible. Maybe you have an explanation.
Yeah, I think maybe I overgeneralized when I was explaining it. So it is possible when you're doing active remote sensing. I didn't talk a lot about active remote sensing, but that is where, as exactly as you say, you send out a pulse from a laser or something. That laser pulse goes down, it's reflected, it comes back. You know the time it takes for travel, and therefore you can infer the distance and therefore where vertically that reflection was made. That does exist. There are instruments that do that, but they're relatively more rare, and they're limited in terms of they only look specifically right below where the instrument is, and so it's basically a point measurement moving across the Earth's surface, but still sort of a point by point measurement of this vertical position, and it's only the top level of the cloud or the smoke plume, for example. Once the signal gets reflected back from the top of that smoke plume, you don't necessarily know, does that smoke plume go all the way down to the Earth's surface, or is it in a specific layer of the atmosphere, because you're only seeing the top of it. So that's one aspect. With active remote sensing, you can do that, and that has been done. And I didn't make that clear. But with passive remote sensing, I think the limitation is you're relying on the sunlight, and the sun is constantly emitting this radiation. So you don't know the travel time. You don't know when the specific photon originated at the sun and came out. So you don't get that kind of information. Whereas if you send the laser pulse, you know specifically when you sent that laser pulse. So that's for passive remote sensing. We can't do that. What we can do with passive remote sensing is the multi-angle, what I was mentioning, the Maya mission, the multi-angle imager. By looking at different angles, you will get some information about that vertical, because at a specific angle, you're seeing a specific slice maybe of the atmosphere more clearly than other slices. And as you move at different angles, you can get some of that information more so. Again, I think it's a little bit limited just to the top, that you might see the reflection from just the top level. So the way that this can be addressed in a couple different ways, if you have a model that you think is capturing the vertical profile relatively well, maybe it gets the total amount wrong, but it's getting the vertical distribution correct. You can get the total amount from the satellite and the vertical distribution from the model, and then combine those two together to estimate what the vertical distribution is. That's one approach. You can use the ground-based instruments. So if you have sort of a satellite looking down and something on the ground looking up, if they're both maybe active sensors, one pulse from the ground going up sees the bottom of the layer, the pulse from above sees the top of the layer, so you kind of can constrain at least where the layer is. And there's also, maybe more sophisticated, radar and LiDAR type systems, which can actually see, maybe into the layer a little bit using different parts of the spectrum. So I think it's possible to do. It's not as common. I would say, still currently the most common technique is the passive remote sensing, because it gives you this wider area coverage with a single view. You can cover more of the Earth's surface. I think yeah, I'll leave it there. It's possible, but it's less common, and it's a little bit more difficult, I think.
Okay, I just want to maybe contribute to that. I'm aware that we have Calypso, or the Calliope, or even the Iolo satellite, which is able to determine missing layer heights And with that, you're able to get the vertical resolution of whatever layer of dust you have there. So the Calliope and the Calypso, together with the IOLO satellite, are able to help in studying the vertical levels of the aerosols.
Yeah, exactly. That's an example of an active instrument. I believe, unfortunately, that that data set's been discontinued. The instrument was turned off, but the historical data is still available, obviously.
All right, so that's all we have for time for. So we'll just go ahead and thank Carl one more time, please. Sorry, we have to move on. Yeah. I believe we already have your slides, so we will share them if that's okay with you, Carl.
Yeah, please do. I put a PDF version, which might be a little bit more manageable, and I think my email is in the slides as well. If not, I'll provide that if people have follow-up questions.
Okay, cool. Well, thanks a lot.